Welcome back. In the next part of this lecture, we'll be talking about evaluating functions, both evaluating them numerically and also evaluating them symbolically, evaluating them with some expression involving variables. So to begin with, when we talk about evaluating a function, we're talking about taking that function and finding out what would be the corresponding y value for a particular value of x. And that means that we could, for example, evaluate this function f of x equals to x squared and find out what is the value for y when x is 3. And if we're doing that, we're finding out what f of 3 is. That's what f of 3 represents. This represents the y value when x is equal to 3. In general, whenever we're thinking about f of x, we can always be thinking about it as the y values for our function. So when I say f of 3, that's the y values for our function when x is 3. And of course, we know how to do this. We've put in 3 for x. If the original function was x squared, then it's the 3 that's getting squared, and that gives us 9. So for this function, the value of f of 3, the value of our function, is 9. But of course, you can also evaluate a function with an expression. So the same function that I have, f of x being x squared, maybe I'm interested in what is f of a plus 1. What happens when I take my function and replace x with a plus 1? A couple of things just to note here. One thing, which hopefully is not a surprise, is that when we're evaluating a function with a number, we find a number as our value. So when we put in a number 3 for x, we got a number 9 for y. And also not a surprise that when you're evaluating a function with some expression involving a variable, you'll get some expression involving that variable as your corresponding value for y. The other part to notice here is my use of brackets. So here, in the first part, it wasn't as crucial. It was just x squared, just a single thing being squared. And so for f of 3, we just made sure that we squared the 3. But I was being pretty careful here myself, making sure that I wrote brackets around the 3, just to set the scene for what comes next. That when we're looking at f of a plus 1, that's saying that we'll be replacing the x's with a plus 1's. And since in the original x was being squared, then I want to make sure that when I replace x with a plus 1, that all of that is being squared. That's the reason why I have for f of a plus 1 that it's not just a squared plus 1 or a plus 1 squared or some other type of thing. I want to make sure that the entire input is being squared because that's what my function is supposed to do. My function says that it's going to take whatever you give it as the input and square that input. So if we put a plus 1 as the input, then a plus 1 needs to be squared. And there we go. The next thing that I did was just to evaluate that by expanding a plus 1 times a plus 1, and that gave me a squared plus 2a plus 1. So we've got a function here, a nice little polynomial function, f of x being 3x squared minus 2x plus 1. And now I want to evaluate. So f of 0, this is just asking me what's the y value when you replace x with 0. So that would be 3 times 0 squared minus 2 times 0 plus 1. And this is just a nice little calculator moment. We find that f of 0 is 1. Or in other words, if you're thinking as a graph, that the point 0, 1 would be on the graph of f of x. F of 2, we're just going to replace all of those x's with 2's. And same thing here, just grab my calculator and do a little bit of calculation on the side, and I find that f of 2 is 9. Okay, so for the next ones, now we're getting into things where we're going to be evaluating things symbolically. So we have here, for this expression, we want f of x plus f of 2. And we know what those things are individually. F of x, that's the original function as it was given. And f of 2, we just figured out what f of 2 is. F of 2 is 9. So if we want to say, well, what is f of x plus f of 2? F of x is 3x squared minus 2x plus 1. And f of 2, we just figured out that that was 9. So together, f of x plus f of 2 should be 3x squared minus 2x plus 10. Now compare this part C with part D. They look similar. They both have x's and 2's involved. One of them is f of x plus f of 2. The other one is f of x plus 2. And the difference between them is, although there's x's and 2's for both, in part D, we're seeing that we're going to take our original function and replace all of the x's with x plus 2's. So when I find f of x plus 2, what I'm going to do is take my original function, which was 3 times the input squared minus 2 times the input plus 1. My original function, that's what it was, 3 times input squared minus 2 times whatever the input is plus 1. And here we want our input to be x plus 2. And again, notice that I use brackets because in my original function, I want that whatever the input is, that the whole input gets squared before it gets multiplied by 3. And so that's what I've made sure is happening down below, that the input of x plus 2, that whole thing will get squared, and then it will get multiplied by 3. I need those brackets because if I didn't have brackets, then it would only be the 2 that would be being squared, not the x. And I want to make sure that the entire input of x plus 2 is being squared. So now we just need to finish this off. And for this, I'm just going to expand. X plus 2 squared would be x plus 2 times x plus 2, which, if you were to multiply that out, would be x squared plus 4x plus 4. And then just expanding a little bit further. So we'll have in this next part, I'll have 3 times x squared. I'll have 12x minus 2x. That would be 10x. And I'll have plus 12 minus 4 plus 1. That turns out to be 9. So there we go. When we take f of x and replace all of the x's with x plus 2's, we get 3x squared plus 10x plus 9. Again, not a surprise that since we're evaluating involving things with x plus 2's, that we'll get an output that will still involve x's. If we evaluate our function using some variables, then those variables will likely show up in our output. All right, just a couple more to do. F of negative x, this would be taking all of our inputs and replacing them with negative x. So our original function was 3 times the input squared minus 2 times the input plus 1. And if I replace all the x's with negative x's, then in the first term we'll have 3 times negative x squared, and negative x squared is the same thing as positive x squared, so we'll have 3x squared, minus 2 times negative x, that's plus 2x, and plus 1. For the next one, we have two things to do. So here, notice that there's a minus, a negative out front. So two things. Number one, f of 3x, that's taking our original function and replacing all of the x's with 3x. And then once we found that, we're going to be multiplying that all by -1. So that means we'll have -1 multiplied by f of 3x. F of 3x, we'd find that by taking our function and replacing all the x's with 3x. And if we were to evaluate inside the brackets there, 3x squared would be 9x squared, and multiplying that by 3 would give me 27x squared. Minus 2 times 3x, that's minus 6x. And then finally, we have the negative that was in front. We're now going to do that multiplication. So multiplying everybody by -1, that gives me negative 27x squared plus 6x minus 1. All right, finally, one last thing for us to do here, f of x plus h minus f of x, which is actually something that's going to be pretty important in one more slide after this. So this expression, f of x plus h minus f of x, means that we've got two things. Number one, we'll have to find out what is f of x plus h. And then once we do that, we'll then subtract f of x, our original function, from it. F of x plus h, we'll figure that out by taking the inputs and replacing the inputs in our function with x plus h's. And then now minus f of x, and that's just going to subtract the function as it originally was written. Now, the only thing left for me to do here is just to do a little bit of expanding and simplifying. That first bracket that I have on the left side, I have inside of it x plus h squared, which if you were to expand that, that's x plus h times x plus h, which is x squared plus 2 times x times h plus h squared. And then multiplying out in the next bracket, minus 2 times x plus h. And then lastly, what I'm going to do here is just carry that negative through my second bracket. I'm subtracting f of x, so that would give me negative 3x squared plus 2x, and then minus 1. And you'll be able to see in the next line that a lot of things are now going to cancel. Just multiplying that 3 into the bracket there. There we go. And we can see that the 3x squared and the minus 3x squared are now gone. Minus 2x and plus x are gone. I have a plus 1 and a minus 1 that are now gone. So f of x plus h minus f of x, that simplifies to just give me 6xh plus 3h squared minus 2h. And there we go. So again, not a surprise that there are x plus h's in my final result because, of course, we evaluated f of x plus h. So we're expecting to see x's and also h's. All right, so the idea of a difference quotient is something that we're going to see in this course more or less as a preview of something that you will see in calculus. So whatever plan you have for the future, whatever version of calculus you're planning to have, whether it's calculus for physical sciences or calculus for life sciences, the idea of a difference quotient shows up at the beginning of that course, and they'll be doing something a little bit different with the difference quotient. For us, there's really only two things that we'll need to know about it. Number one, what is it? And what it is this expression, f of x plus h minus f of x, whole thing divided by h. And of course, I've got that little excluded value there. Obviously, h can't be 0, otherwise that would be undefined. What it represents really is the slope of the line that passes through a curve at 2 points. So here, if you're imagining this little parabola that I've drawn in black, I've chosen 2 points. So I have 1 point when the x-coordinate is whatever it is, x, and of course then the y-coordinate would be f of x. And that my second point I find by going h units to the right. So the next x-coordinate is x plus h, the original x-coordinate plus h units more. So that means for my second point, the x-coordinate is x plus h, and the y-coordinate is f of x plus h. And if you're thinking about slopes, you know that the slope is just the change in the y value divided by the change in the x value, which in the numerator you would have f of x plus h minus f of x. And in the denominator you would have x plus h minus x. The x's would cancel and you would just have h. So that's what the difference quotient is. It's just the slope of that straight line. That's as far as we need to know about it for now. Like I said, you'll be doing something a little bit further with this when you get into calculus. For us, we just need to know how to find and simplify a difference quotient. And so for us here, there's one important thing to mention, which is what do I mean by a simplified difference quotient? And so the thing to remember is that what we'll be doing is to simplify a difference quotient means do some sort of algebra until you can get to the point where the h that was in the denominator can be canceled. So for our difference quotients, this is the idea here. We want to get it to the point where the h can be canceled, the h that was originally in the denominator, and once we've done that, now it's simplified. So we're going to do this here, finding and simplifying the difference quotient for these functions. First one, g of x. So if we're looking at our difference quotient using g of x, we know that the difference quotient would be g of x plus h minus g of x whole thing over h. And to find g of x, or g of x plus h rather, we're going to be taking our original function and replacing the x's with x plus h. Now notice here that when I put in x plus h, when I replaced it with x, I put it in brackets, and the reason for that is in the original function, the input is being multiplied by 2, so for g of x plus h, all of x plus h needs to be multiplied by 2. So therefore I'm going to be putting that in brackets. I don't want to just have just the x's multiplied by 2. I want the entire input, which is x plus h, multiplied by 2. And if I just simplify that a little further, here I've got 1 over 2x plus 2h plus 1, and 1 over 2x plus 1. All right, so far so good. Now, the goal here, of course, is to get it to the point where this h, the one that we originally had in the denominator, can be canceled. And so my plan here is to first just simplify this fraction. So if you're thinking about how would we do this, we've done things like this in the past, where we have a compound fraction, fractions inside of fractions. And the plan that I had was that I was going to think about what would be the common denominators for these fractions, the fractions inside the fraction, and multiply everybody top and bottom by that common denominator. So what I'm going to do is multiply all the terms on the top and on the bottom by 2x plus 2h plus 1 times 2x plus 1. All right. And so this is going to do a couple of things for me. The important thing that it's going to do for me is that when I multiply this expression by the first fraction, the denominator, the 2x plus 2h plus 1, will cancel. And same thing with the second fraction, the denominator here will also cancel. In the bottom, I'll have these three things, the h and these other two factors, all multiplied together. I'll just leave them as is. I'm not going to expand them out. I'm just going to leave them lying around the way that they currently look. And the reason for that is, remember, my goal is to eventually cancel out this h. So why would I multiply it together with a bunch of things? I'll leave it out and factored. That way it'll be easier for me to do my canceling. All right, so now I'm just going to add myself an extra page here. And let's continue on. So as I said, I'm going to multiply top and bottom by that common denominator. And so that means that in the numerator, I'll have 1 times 2x plus 1. And there'll be a minus 1 times 2x plus 2h plus 1. And on the bottom, I have 2x plus 2h plus 1. I have 2x plus 1. And I have the h that I'd originally had. Okay, so now I just need to simplify the numerator, and if you were to simplify this, you'd see that you would have a 2x and a minus 2x that would cancel. You would have a 1 and a minus 1 that would cancel. That the only thing that would be left in our numerator would be a minus 2h. And at that point, you can see that, yes, the h that we originally had in the denominator has now been canceled, which means that what we have is simplified. This is one place where people might want to do more work, and really we should resist doing extra work if we don't have to. The more work being expanding these out. Some people will feel that they're obliged to now multiply these together. No, you're not. Remember that in general, we want to leave things in factored form. So even if I didn't say leave your answer in factored form, this is the nicer way to leave it rather than actually multiplying everything out. So this would be my final answer then for my simplified difference quotient, negative 2 over 2x plus 2h plus 1 times 2x plus 1. We're going to do one more difference quotient here. And so for this, we're going to take f of x, our function, and find the difference quotient. So that's f of x plus h minus f of x all over h. So we'll have root of 2 times x plus h plus 3 minus root of 2x plus 3 all over h. And same thing as before, when I'm replacing my x's with x plus h, I do so by putting the x plus h in brackets, because in my original function, the x is being multiplied by 3, so that means in my difference quotient, I want the x plus h. Sorry, being multiplied by 2, rather, in the original function, so I want x plus h to be multiplied by 2, and that's why I've put x plus h in brackets. And then I've expanded it out, so I now have root of 2x plus 2h plus 3 minus the root of 2x plus 3, and the whole thing is over h. Now, at this point, you're looking at this and thinking that my goal is to eventually cancel this h, the h that's in the denominator. And the problem that we have, of course, is the numerator. There's not much that I can do with one square root minus another. This is one place, and this is the only place in this course where we will probably leave our answer with square roots in the denominator. And the reason I'm saying they're going to be in the denominator is that the only thing I can really do to modify what I currently have would be if, let's say, I decided to rationalize the numerator to get rid of the roots in the numerator and move them to the denominator. Normally, that's not what we want to do, but in this case, you'll see in a moment that that actually will allow us to get rid of our roots in the numerator and then cancel the h that's in the denominator. So just like I would normally do if I was looking to rationalize something, I'd multiply top and bottom by the conjugate. So that's what I'm doing here. I'm going to multiply top and bottom by root of 2x plus 2h plus 3 plus root of 2x plus 3. And that when I multiply top and bottom by the conjugate, in the numerator, that's going to simplify things really nicely for me. I'll have the first thing squared, the root of 2x plus 2h plus 3 squared. Minus the other root squared. And in the bottom, I'll have h times the one root plus the other. And same advice that I gave in the previous question, which is you might be tempted to try to multiply the h into the brackets here and combine things together somehow, but remember that the goal is to eventually cancel out that h, so there's no real point trying to combine it with other things. Leave it factored out and we'll be much happier in the long run. So I'm just going to clean up my numerator now, because once I have taken that root and squared it, that gets rid of my root. So that means that what I'll have in the numerator should be, and I'm just going to add one more page here. We should have in the numerator 2x plus 2h plus 3, and then minus 2x plus 3 all over h times root of 2x plus 2h plus 3 plus the other root of 2x plus 3. There we go. So nothing really fancy has happened here. I've just gone from the last line and actually squared the square root, which got rid of my square root. And that means that a bunch of things are now going to cancel. The 2x minus the 2x will cancel. I'll have a 3 minus a 3 canceling. So in my numerator, I'll have just 2h left behind. And the h's cancel. And as I said before, with difference quotients, what we mean by simplify is get it to the point where the h that was in the denominator has canceled, and that's where we're at. So this is where we'll leave things. This is something I want to draw a nice little star beside just as a reminder. This is the only time we leave roots in the denominator. Would be this specific instance. If we're doing a difference quotient and it's something involving a root, and once we've canceled the h, there are still roots in the denominator, that's actually the only time in this course I'll say that yes, please leave things as they are. And the reason I'm saying this is, with the wisdom of having done these sorts of questions a bunch of times, I can tell you without actually having to do it that if you were to take this expression and try to get rid of the roots that are in the denominator, if you tried to rationalize the denominator, all you'd wind up doing is going back to the original first line that you'd had. Basically, it would undo all of the work that you'd done and you'd go right back to the beginning again, which is not what you want to do. So this, as I say, this is the only place in this course where it's fine for you to leave roots in the denominator. And in fact, you kind of have to, because if you tried to get rid of those roots, that means you'd reintroduce the h that you just got rid of, and you basically would have undone all the work that you've done. So this is the spot where we'll end with this problem.